So let's talk about mass-energy equivalence. This is a consequence of Einstein's theory of special relativity. Now, I'm not going to go into all the background as to why it's true, but we'll talk a little bit about what it means. So it means that mass is concentrated energy. So whenever you have mass, it means you've got lots and lots of energy just kind of sitting there. How much energy? It's given by Einstein's famous relation, E equals mc squared. M is the mass, which we'll put in kilograms. And c is the speed of light in a vacuum, which is approximately 3 times 10 to the 8 meters per second. 300 million in SI units. And I'm going to square it? No wonder we are saying that mass is concentrated energy. This number is huge. So, for example, a 20-gram marble, just little marble, 20 grams, contains the same amount of energy as is released in the explosion of a 500,000-ton hydrogen bomb. A little marble like that. So why aren't we afraid of marbles? Well, this energy is really, really, really difficult to release. Very difficult to release. So if you've got a marble sitting there, there's almost no way that you could release all that energy. The only way that there is to release all of that mass energy is through something called matter-antimatter annihilation. So we've got matter coming in, antimatter coming in, all the energy is released from both of them. Matter and antimatter both have mass, but there's not a lot of antimatter around. Very little. So we do have anti-electrons. So let's just look at this process. I've got a positron, which is an anti-electron, and an electron. They come together and annihilate and just produce energy. This gamma means photons, which basically just means energy for our purposes. So how much energy is released? Well, the mass of an electron or a positron is 9.11 times 10 to the minus 31 kilograms. So the energy that's released, 2 mc squared, because I got it from the electron and from the positron. And that turns out to be 1.64 times 10 to the minus 13 joules. It's not very much, but that was 2 electrons. Well, an electron and a positron. Think about it. If you've got a mole of these suckers, that's a lot of energy. Turns out to be about 10 to the 10 joules for 1 mole of electron-positron pairs. All right. So what does this actually mean? We're not going to do this matter-antimatter conversion because there's not enough antimatter around. It turns out that almost every single release of energy actually can be understood in terms of this energy-mass equivalence. So let's look at chemical energy. All right. So water is a molecule. It's formed by taking 2 hydrogen atoms and an oxygen atom and making 2 bonds. Bond between oxygen and hydrogen, bond between oxygen and the other hydrogen. These bonds cost energy. How much energy? 918 kilojoules per mole. So that means that there's about 1.5 times 10 to the minus 18 joules of bond energy per molecule. Now what we can do is we can use this to indicate that the mass of a water molecule is slightly less than the mass of hydrogen times 2 plus the mass of oxygen. The difference is associated with the mass of the bond energy. So how do we get that? Well, we're going to say, okay, the change in mass is, or the energy is given by the change in mass times c squared, because E equals mc squared. But we're not going to use the whole mass because we're not destroying the hydrogens and the oxygen. We're just destroying the bonds. So you can think about it like the mass of the bond itself, okay? And it's just associated with that energy. Now, we don't talk about that in chemistry because this change in mass divided by the mass is like 10 to the minus 10. That means in order to even see the difference in mass between water and 2 hydrogens and an oxygen, we would need to write out 10 digits in the mass. And the only difference would be out there in the 10th digit. Nobody cares about that. So that's why we don't talk about it that way. We just talk about the energies. All right. So this is the way that we usually see Einstein's relation. Energy is equal to a change in mass times c squared. What's the difference in mass between what did we start with, what did we end with? Multiply that by c squared, and then you got the energy released. All right, in nuclear reactions, it's a bit of a larger situation. We've got, for example, the alpha decay of uranium-238. So uranium-238 goes to thorium-234 and helium-4. Now, if you add up the mass of this helium nucleus and this thorium nucleus, you get a smaller mass than the mass of this uranium nucleus. Smaller by how much? Well, again, it's not by a lot, but the change in mass over the mass, so this is the relative mass, turns out to be about 2 times 10 to the minus 5. Well, it's still small, but it's 5 orders of magnitude bigger than the chemical energy release. So that's one way that you can understand nuclear reactions releasing so much more energy than chemical reactions. Because the fraction of the mass that's released in terms of energy is 100,000 times greater. All right. So what about other processes that we could use to release all of this untouched energy? Well, neutron stars and black holes are probably our best bet for releasing the largest amount of this mass energy other than matter-antimatter annihilation. It turns out that with a neutron star, you can get relative releases of energy of order 7%. So that's 0.07 versus 0.00002. All right? So that's a huge amount of energy. And with some types of rotating black holes, you can get it up to almost half, 42%. So that's Einstein's energy mass relationship, and it's really, really, really simple. All you need to do is multiply by the speed of light squared. That's it.